Hey everyone, and welcome back to Quesadilla Math with me, Mr. Padilla. Today we are going to be talking about solving systems of linear equations using matrices, specifically using the inverse matrix to help us solve. So, let's get started. In order to solve a system of linear equations using matrices, first we have to learn how to convert a system of equations into a matrix equation. The first thing that you need to pay attention to are the different parts of our system, namely the coefficients, the variables, and the constants. Each of these separate pieces is going to form its own matrix. In this case, we have a system of two equations with two variables, x and y, and you should definitely notice that both of these equations are in standard form, where we have the coefficient times x plus or minus the coefficient times y is equal to the constant. Both of your equations need to be set up in this way so that you can create the matrix equation. To start off with, you're going to make a matrix of the coefficients. The coefficients, in this case, make this 2 by 2 matrix. Then we also make a matrix using our variables. Notice that this matrix is a 2 by 1 matrix, so that when we multiply this 2 by 2 matrix with this 2 by 1 matrix, we end up with 3x plus 2y and 6x plus 5y. Finally, we make the constant matrix that was made up of our two constants, -3 and -12. Always make sure that you look out for making little mistakes like that. A dropped negative in a matrix algebra equation can be the bane of your existence. You can make a matrix equation to model a system of equations of any size. In this case, we have a system of 3 equations with 3 variables. So we can turn it into this matrix equation. As you can see, since this is a 3 by 3 system, we end up with a 3 by 3 matrix times a 3 by 1 matrix equals to another 3 by 1 matrix. Now, how do you actually use a matrix equation to solve for these variables? Well, in a way, it's similar to solving a regular algebraic equation. Let's take, for instance, the linear equation 3x is equal to 12. Now, to solve for x in an equation like this, really, you should know that you can divide both sides of your equation by 3. Now, the reason we divide by 3 is so that we can cancel out the 3, that's the coefficient of x in this equation. But really what we're doing is really dividing 3 by 3, which equals to 1, leaving us with just 1x is equal to 12 divided by 3, which is 4. Of course, we never just write 1x, we usually just leave it as x equals 4, and we consider this to be the solution to this equation. The problem with a matrix equation is that you can't just simply divide a matrix, such as our 3 by 3 matrix, so that way we are left with our 3 by 1 matrix x, y, z equals to some other matrix. Instead of dividing a matrix, since we can't do that, we have to use another tool. We call this tool the inverse of the matrix. Let's talk a little bit about how to find the inverse of a matrix so that we can use it to help us solve our system of equations and this matrix equation. So, the identity matrix is a type of matrix that acts like the number 1 in a regular algebraic equation. Let me show you what I mean. So the identity property of real numbers lets us take a number such that it's not 0, and if we divide it by itself, it equals to 1. If we take the number 1 and multiply it with some number, that number stays the same, otherwise known as keeping its identity. So this is why we call it the identity property. Now the inverse matrix works in a very similar way. The identity matrix is a special matrix such that when you multiply it with another matrix, that matrix does not change. The rule here, if we take a matrix A times I, what we call the identity matrix, we get that same matrix back, A. Now, what does the identity matrix look like? The identity matrix takes different forms depending on what size matrix you're trying to multiply it with. No matter the size, the identity matrix is such that you have only ones and zeros as your entries, where the 1 only appears one time in each row, and it changes places each time. So for a 2 by 2 identity matrix, we have the matrix 1, 0, then 0, 1. If we are using a 3 by 3 identity matrix, we have the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. If we're using a 4 by 4 matrix, we have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now, this continues ad infinitum for a matrix of any size. You can have a 5 by 5 identity matrix, 10 by 10 identity matrix, whatever size identity matrix you need for the particular operation you're trying to do. So let's see how the identity matrix actually works to keep your matrix the same even when you multiply by it. So for this example, I'll be multiplying the 2 by 2 matrix 1, 2, 3, 4 by the identity matrix 1, 0, 0, 1. Multiplying these two matrices results in where we have 1 times 1 plus 2 times 0 for row 1, column 1, 1 times 0 plus 2 times 1 for our row 2, column 2, 3 times 1 plus 4 times 0 for our row 2, column 2, and 3 times 0 plus 4 times 1 for our row 2, column 2. Now you'll notice that everywhere we're multiplying by 0, well, you'll just end up with 0. So 2 times 0 becomes 0, 1 times 0 becomes 0, 4 times 0 becomes 0, 3 times 0 becomes 0. And all of the remaining numbers are only being multiplied with 1. So we end up with the exact same matrix that we multiplied with the identity matrix, 1, 2, 3, and 4. So the identity matrix is like the number 1 in the world of matrices. Now, how does this help us to solve systems of equations? Well, now we need to talk about the inverse of a matrix. The purpose of an inverse matrix is to cancel out a matrix that you're using. So you could think of it as kind of like the reciprocal of a number in multiplication. So if I take 3 times its reciprocal, 1/3, it equals to 1. So the inverse of a matrix works the same way. When you multiply the inverse of a matrix with its original matrix, you end up with I, the identity matrix. Let's try to find the inverse of matrix A here, which is equal to 4, 7, 2, and 6. Now, there are different methods to finding the identity matrix, but for our purposes in this Algebra 2 series, we're going to be using desmos.com/matrix to help us find the inverse. So let's go over there and see how this works. Here at desmos.com/matrix, we can learn how to input a matrix into the calculator and then find its inverse. So the first thing that we're going to need to do is click on New Matrix. So it's going to set us up with the matrix A. And right now we have a 2 by 2 matrix. This is what we need to use, so we don't have to change it, but you can change the number of rows and columns with these buttons down here. Now let's go ahead and enter in our matrix for A. You can use the virtual keyboard here, 4, then 7, then 2, then 6, or you can use your own keyboard on your laptop or your phone. You can go ahead and click enter to enter in this value for the matrix A. Now to find the inverse, we need to use the inverse notation. We're going to go ahead and type in A, and then this is a symbol for the inverse of A. It's A seemingly raised to the -1 power. This is the same way that you show a reciprocal of a number, raising it to the -1, so it matches that notation. So we're going to go ahead and click on that, and immediately we get the inverse matrix: 0.6, -0.7, -0.2, and 0.4. I personally am not a fan of using decimals, so I'm going to click on the fraction button to convert this to a fraction. To prove that this is really the identity matrix, let's take the identity matrix A inverse and multiply it by our original identity A. And when we type that in, you immediately get that it's equal to our identity matrix, 1, 0, 0, 1. Now we can say that our inverse of matrix A inverse, is equal to 3/5, 7/10, -1/5, and 2/5. Let's try another one. This time we're going to let this 2x2 matrix be called the matrix B, 3, 6, 1, and 2. And let's see if we can find B inverse using the matrix calculator. So after entering in our matrix B, we can go ahead and type in B raised to the -1 power, B inverse. And it seems like we have a problem. If we hover over this exclamation point, we see that we get a little error message. It says singular matrices do not have an inverse. This has no solution. So a matrix that is not invertible is what we call a singular matrix. And a matrix that does have an inverse, we call a non-singular matrix. Now that we know about the identity matrix and the inverse matrix, we can use these concepts to help us solve a system of linear equations as seen here. So our system is -2x plus 6y equals -10, and 3x minus 8y equals 12. So first things first, let's create the matrix equation. So we'll have our 2x2 matrix made of the coefficients -2, 6, 3, and -8. Our variable matrix with x and y, and our constant matrix with -10 and 12. For our purposes right now, we will go ahead and call our 2x2, our coefficient matrix, matrix A. So let's go ahead and find the inverse of matrix A using our graphing calculator. Using our Desmos calculator, we get A inverse is equal to 4, 3, 3/2, and 1. Now we can use this identity matrix to cancel out our matrix A, turning it into the identity matrix, like so. Just like in an equation with normal variables, what you do to one side of the equation, you have to do to the other. So here what I'm doing is I'm taking my inverse matrix A inverse times matrix A. Notice how I put it in this order: the inverse, then the original matrix. On the other side, I also have my inverse matrix times the constant matrix. Notice that it's also on the left side of it. Since here we have a 2x2 matrix and this is a 2x1 matrix, they actually can only be multiplied in this order. You can't multiply a 2x1 matrix with a 2x2. So you must make sure to be really cautious how you do that. What's great about multiplying our inverse matrix with our original matrix A is that these become the identity matrix 1, 0, 0, 1. And when we multiply this identity matrix, I, times our matrix xy, we're just left with that matrix xy. So to find out what it equals to, we have to multiply our inverse matrix A inverse with the constant matrix -10 and 12. To do that, we're going to go ahead and use the matrix calculator on Desmos again. After multiplying, we get that the matrix xy is equal to the matrix -4, -3. Now, because these matrices are equal to each other, we can also assume that the corresponding entries are equal to each other. So we have our solution to the system, x equals -4 and y equals -3. So now let's look at the beauty of really using the inverse matrix here method to solve the system of equations. Now in this case, we have a system of 3 equations with 3 variables, and wouldn't you know it, they're loaded with fractions. So this is a prime example of why we like to use matrices to solve certain complex systems of equations. Let's start off by creating our matrix equation. So we get the 3 by 3 matrix A times our variable matrix x, y, and z is equal to our constant matrix 7, -8, and 7. Now let's go ahead and use the Desmos matrix calculator to find this matrix. I'm actually going to show you this time so that way we can practice putting fractions into the matrix. So we can clear everything from our last problem and create a new matrix. It'll once again set us up with matrix A, except this time we need to make it a 3 by 3 matrix, so 3 rows and 3 columns. To input a fraction, all you really have to do is type in the division symbol. So to type in 1/2, we'll put in 1 divided by 2. Then we can go into the next space. So once you complete the entire matrix, all you have to do once again is type in A inverse, and we get our inverse of matrix A, which actually is a pretty nice looking matrix. -5, -4, -3, -1, -2, +1, -3, -1, and -2. So once again, you need to take the inverse matrix, the inverse of A, and multiply it on both sides of the equation, remembering to keep it to the left of each matrix. When I multiply matrix A inverse with matrix A, these will cancel out or give us the identity matrix. And multiplying the identity matrix with matrix XYZ will just leave us with the matrix XYZ. Once again, using that matrix calculator, we will go ahead and multiply these two matrices together, and we will get the solution. XYZ is equal to -24, 16, and -27. I hope you can take what you learned today and use it to help you get out of the matrix. If you enjoyed this video, please leave a like and subscribe for future videos. And as always, I'll math you later.